let's get started. So my name is Carlo Giacometti. I work in the sound and vision team for Wolfram. And today I will talk about video generation and the new functionality that we introduced between version 12.3 and version 13 towards ease of generating videos in notebooks. I will keep an eye on the chats during the presentation. If it is particularly relevant, I will respond immediately. If not, I will answer after the end of the presentation. My plan is to first introduce the ideas behind this, why we're doing this, what kind of targets we want to hit. And then quickly go through some of the functionality, the new functionality that can be subdivided between functionality that takes video or videos to produce another video, functionality that takes generic expressions to produce videos, and a special one that you have seen probably already if you have seen Stephen's keynote or Shadi's presentation that involves exploration of 2D constructs. And as a last thing, I will quickly give an overview of what our generic plans for the future in this subfield are. So in previous versions up to 12.3, our development was mainly focused on producing a framework to be able to perform basic operation on videos, very low level. And we can classify these as structural operations. In this case, I'm just showing trimming a video and joining a video with itself. So extremely basic operations. Hopefully we'll evaluate quickly. We have facilities to combine tracks of various kind, deleting parts of videos, replacing parts of videos. Another broad category are operations that involve processing or analysis. And one example of processing is, for example, video map that takes a video and produces frames, in this case, depending on both the frames and the audio track of the input. An example of pure analysis is using video map time series, where I can essentially map an image processing function, in this case, backed by machine learning, onto the frames of a video. In this case, I want to figure out how many cars are in each frame, and then plot the result as a number of cars as a function of time. In addition to processing and editing operations, we also introduced some functions to do very low-level video generation. And the single function that was doing this was video generator, which is a bit of an obscure function. It is not particularly user-friendly, but it provides all of the basic functionality to generate videos. In this case, I just pass it a list of images, and it will create a video with those sequence of images. But it can be much more general than that. I can just give it a pure function. As you can see here, the function is a function of the actual time in the output video. And this function produces an image per each of those times. So you can see this is a working video. But as I said before, this is a very low-level operation. So what we wanted to enable the users with was for version 13 to have much higher level functionality to generate videos. Also with syntaxes that they are familiar and they don't have to go to so much effort in figuring out the details of. We want to make video creation easy and natural. So however you're creating your content, it should be as easy as possible to transform it into a video that then you can either embed in a notebook or share on the internet or whatever you want to do with a video. So I will start with the video-to-video category. And the first function in this category is snippets video, where the whole idea is extremely simple. We have a video as an input, and we know of a list of times that we think are important, either because we looked at the video or we ran some processing on the video, and that processing spit out a bunch of numbers. So we start on the assumption that these times are salient times. And what snippet video does is just extracts some amounts of video around these times to create kind of a summary of the initial video. This might take a little second, but hopefully not too much. By the way, I am wrapping everything in this notebook with animated image. So the outputs that you see will be actually embedded in the notebook rather than being files that live on my hard drive. This way, the notebook is shared in the page on Pathable, and these outputs will play on your machine as well, that they are completely contained within the notebook. So hopefully that will show up. And yeah, the only thing that this did is extract some snippets around these salient times and join them together in a final video. We are also working on different algorithms for automatic detection of salient times, and that will enable us to have the snippet videos with a single argument. We are not there yet. Hopefully we'll get there by 13. But yes, this is the ultimate goal of the function, where with a single argument, you can either do a random extraction, a uniform extraction, or a salient times extraction. The second function I want to show that goes from videos to video is grid video, where the goal is to create a collage of synchronized videos. In this case, I just give it a flat list with 2 inputs, and grid video will produce a single one with the 2 that are playing completely synchronized. And the nice thing is that these could have wildly different frame rates, wildly different resolutions, and grid video will take care of all of that and will produce something that has a sensible frame rate with which it is easy to display both of the contents. And by default, grid video will try to arrange a list of videos into a matrix. Here, we only had 2 videos, so really having them into a matrix doesn't make sense. But for a longer list, for example, here, I have 5 videos. You can see these are nicely arranged into a grid. It is also possible to control the background of this grid and the spacing. So if you want some more space between the videos, if you want to control the background, that is easily modifiable with options. And the other nice thing is if the user wants in-depth control of the positioning of a specific video in the final grid, you can input a rugged array. It doesn't need to be a rugged list. It doesn't need to be a rectangular array. This can be just a list of lists. Each list can have its own independent length. Grid video will do something sensible and inject spacers where it thinks it is reasonable. As for these spacers, if you have opinions about where they should be, for example, you don't want it here, you want it in a completely different spot, you can control the appearance of those where they live in the grid using missing. Oops, and I shouldn't have evaluated that. That might take a little second. And as you can see, this is a grid that I built, and I placed the spacer in the second row in the first position. You can also use different methods to conform the frames to the size using the conformation method option. And here we can display 3 different methods: stretching, that will deform the image; fit, that will just use whatever is available and leave some spacing on the side; and fill the will just fill the available space. So that's good video. And then the last function in the category of video to video is overlay video, where the goal is to, as the name suggests, overlaying multiple videos or images onto each other. One example is a watermark. Here I have, maybe you have already seen this example in Shadi's presentation, a sample video, and then our beautiful spiky. And the result is exactly as you'd expect. The spiky is placed in the bottom right corner and its transparency is preserved. This overlay can also be a video, which will be synchronized to the background. I will use again my fish video that we've seen already before. Like in grid video, the two are synchronized and the proper temporal resampling is happening as well. It is also possible to overlay multiple objects, and you can also control their position using the place head. So one question is, why was the spiky in the bottom right corner rather than in the middle? Well, that's just a choice of default, right? In many cases, this will be more convenient. In many cases, it will be more convenient to have it in the center, but you can control that very finely using placed. Here, I'm placing the fish at the left bottom and the spiky at the right bottom. And you can do exactly, you can specify any scaled position here. And the two specifications here, if you, I don't know how familiar you are with placed, this will tell you where the expression will be placed in the final result. And this is the reference point in the inset expression. And this accepts a position in points or a scaled position. So it is easy to move these anywhere within the frame. As an aside, I wanted to quickly touch on a few common options for video generation that are available in all of these functionalities. So the first one is related to the encoding of the file. I will show here how to control the video encoding, but it is exactly as easy to control the audio and the subtitle encoding. Depending on your system setup, this list might be different depending on platform, how you set up FFmpeg, et cetera, et cetera. But this will give me a list of what are possible encoders on essentially how we end up storing the frames into the file. And they all have different trade-offs in terms of speed and file size and fidelity to the original content, right? Because most of these will compress the content. And you can choose any of those by using the video encoding in this case, but it will be audio encoding or subtitle encoding in other cases. So you can easily choose one of the most common encodings, H.264, but you can choose more obscure ones like JPEG 2000, which incidentally will allow you to store videos with an alpha channel in most cases. At least support of it is not completely platform independent. Another very important option is the generated asset location option that will tell you where the file backing the resulting video object is stored. By default, we create automatic names. They all get stored in the user documents directory. But that can be controlled function by function and call to call. In this example, I will store the result in new file.mp4. That works. This also takes a folder. So this will be an automatically generated file name in the folder I specified. And if I want to collect all of the video generation in a single folder, I can use the generated asset location, $generated asset location variable. I can set it to a folder, and as a consequence, all of the video generating functions will produce files in that folder. raster size option is pretty self-explanatory to control the size of the output. And most of the generating functions will are enabled to be parallelized. So, for example, this is a slow operation, the rasterization. So the generation of this video will take a little bit. But using parallelize on the video generating function, the evaluation of the function is distributed across the available kernels. So the writing to the file is still serialized. We still need to write one frame at a time, but we can chunk up the generation of the frames and distribute that to all of the kernels available. So this is a very convenient trick to know, especially for video generation that has to deal with rasterizing graphics expressions. So now pure video generation from arbitrary expression. I will go through the first few functions that are pretty straightforward that have been there since 12.3. For example, slideshow video does what the name suggests, takes a list of images and displays each image for a well-defined amount of time, in this case, 1 second. And it is possible to control the duration of each image individually. In this case, we have a short first duration, slightly longer second, and very long last one. And to have more fine control over the result, it is possible to pass a time series to slideshow video. And a time series object that has, in my example, images as values. And this is interesting because the time series by default will have an interpolating behavior. So I'll just chuck this into a manipulate. You can see how the images get interpolated. And by the way, this is because all of our images now support arithmetic operation. So if I pass that time series to slideshow video, I inherit this very convenient interpolating behavior of time series. The second video generation function is called animation video. So the whole idea behind this was to provide much of the same functionality that video generator has, but packaged in a way that is much more user-friendly and much more familiar to a Mathematica user. I would be really surprised if a Mathematica user was not familiar on how to write a table or a manipulate, and the syntax to use animation video is exactly the same. I have a symbol that is defined onto a range and an expression that is then evaluated that depends on that symbol. So I can generate these frames and I can see, as you would expect, a constant image with varying hue. And just to compare this is, as you would expect, exactly the same syntax as you would have for manipulate. Someone is asking if there are performance difference, I'm assuming, between manipulate and animation video. Well, we do have to write to disk. And we need to generate all frames before displaying the result. So the encoding to disk might be slow. And if the expression evaluates to something that is a graphics, then that needs to be rasterized. So that will have a cost. But once it's done, it is just a video file that is completely agnostic on how it was created. So it can be used in any context. As I said before, we follow the conventions of manipulate and table. So same thing. My variable rot goes from 0 to 2 pi, and I am rotating this beautiful white dog that hopefully will evaluate quickly. Now we have a rotating dog. Who doesn't like a rotating dog? And here is the example that I think Shadi has shown. Again, just to reiterate that this is exactly like evaluating a manipulate or a table will have the exact same result. And as I said before, animation video will work with any expression that evaluates to images, but also 2 and 3D graphics, essentially anything that we can rasterize effectively. So here we have some equation that we can solve, and we can have, I think this is a Lorentz attractor, and we can have a sphere following the path determined by this Lorentz attractor. This is a nice video file now that we can export anywhere. As I said before, most of these video generator functions do accept parallelize. So it will speed up significantly the generation. Okay, now a very basic function that can be also very convenient is if we have a bunch of images in memory and we want to just drop them into a file, but not for a specific duration. We want each of the images to be a single frame of the video. Frameless video is the function that we want. We see we created a video with only these 3 frames, unlike slideshow video that would have duplicated these frames for the specified amount of time. And the disadvantage, obviously, is that we need to store all of these files in memory. In this case, I am importing a bunch of files and writing them to disk. The solution to that kind of annoyance is a function that is still in a private context in video, backtick frame table video, that is essentially the same thing. It just does not require for anything to be in memory. So here we go. We generate our 3 frames video and we import the images on the fly. So this just sequentially scans the files and evaluates this expression for each file and writes the output to a video. So the timing will be the same as a frameless video, but the memory usage will be much less. And obviously, this is a small folder with small images, so this becomes kind of irrelevant. But for larger folders with larger images, this becomes more and more performance critical. And parallelize can be used to speed up the operation. And we are planning in one of the next versions to expose this as a system function. Now, as the last function that I want to showcase for video generation is one that does exploration of 2D constructs. This is called TourVideo. I'm sure you have seen it in Steven's presentation and in Shadi's presentation. I will just give you a quick overview on what it does and some of the subtleties on which it relies. So we start with some 2-dimensional construct. In this case, we have our beautiful test image. And we want to explore some details of it. And in this case, I'm just giving a list of positions specified with scale, so I don't have to figure out how many pixels there are and all those annoying things. And this will produce a video that will tour all of the points they give. So as you can see, this is moving around the image and allows us to explore various parts of it. So what are the possible things that we can explore? Well, images, as I've said, in this case, this I think is the example that Steven showed. I can just find the faces in this big image, figure out the best way to pass through all of them. And then with TourVideo, I just give it the image and the list of points. And in this case, I want to go at a reasonable speed. And this will hopefully visit all of these famous physicists. Another potential input is, one question is, does Tour video jump between position in an image or smoothly move between them? Well, it does smoothly move between them. We will implement different methods. So you will be able to control how smooth that is, or if you want abrupt jumps as well. I was saying another potential input type is two-dimensional graphics. In this case, I have a graphics of a polygon of, oh, wow, that is messy, of a polygon of Italy. And here I am just collecting the points that make up that polygon. So if I evaluate that, I will slowly cycle through the border of Italy. You can also take any two-dimensional region. In this case, I have a Sierpinski mesh, and I am selecting these points here that lie on x value that is 0.5, and I can control the position, so I will tour through them, but you can see here I'm also controlling the zoom level at which I am selecting these points and the times. So here, as I said, there is more control than just passing a list of points. I am passing positions, zoom levels, and times. So the result will be something like this. So I will zoom in at each of these iterations. As I was saying, with the second argument, it is possible to specify positions, times, widths, and a rotation angle for each of the points in the path. And in this case, my path is just a spiral with increasing widths. Hopefully this will play. Aha, here we go. You can see how it is spiraling out and zooming out at the same time. And again, there is no constraint about what these points can be or should be. And one funny thing, you can start creating interactive interfaces for this. Oh no, this is the wrong image. Sorry. Let's go with the dog. Let's go with the dog. So I can, for example, plop a bunch of interesting points on this poor dog's head. And this will hopefully create a video that explores those points very slowly and very tinily, I guess. Let's increase that dimension a little bit. So this image can be explored almost interactively by providing a bunch of locator panes. Clearly there is something wrong with it. Sorry, I was trying with the giant example data image. Anyways, so this is the overview of the existing video generating functions. And where do we want to go from now? Shadi mentioned that video generation is something that we want to focus on. We want to make it easy to create contents for users that are already embedded in the Wolfram language, that know how to use them, that might need more ways to either create content from the Wolfram language to share, or create content to embed in notebooks. So the first thing that we will want to do will be expand support for primitives in Tour video. So support for geographics and more two-dimensional constructs. The obvious extension is the same thing, really, but for three-dimensional constructs. The specification of it will be necessarily more complicated because we'll have to take into account camera angles and three-dimensional paths and all of these things. But the idea behind it will be exactly the same. We might want to do morphing video, morphing between images, cinematography videos, where we take different parts of images and apply different effects, for example, like the convergence effect and stuff like that. So we want to really have a set of functionality that will make it straightforward to create video content very easily from the Wolfram language. And with that, I think that's it. And I guess you can easily imagine how this was created. Thank you very much. And I'll have a quick look at the questions. And I think that's it. So why the spike in the bottom right corner instead of middle? I think I already answered that. All this functionality will work with animated GIFs. Yes, they can be imported as videos. So, and videos can be exported as GIFs. So that is definitely true. There is one question from Arben about integration with the language. I don't think we have concrete plans for that yet, but as you say, the precedent that we have for image and audio will make the design of that more grounded, I feel. So I think that's a possibility, not immediately, but definitely something that will be possible in the future. Generated lasso location could be directed to an SSD or RAID. Yes, absolutely. It will speed up a video creation, even though most of the time the bottleneck is not the writing to the file, it is the encoding, which just means running a compression algorithm. So that might help in some cases, but I would bet that the bottleneck will not be actually pumping bytes to a hard drive. Can event series can be used with slideshow video? Yes, yes, that should be, yes. And you can set the interpolation order in time series as well, if I am not mistaken, to have sharp transitions. Does slideshow video allow some choice of transitions? At the moment, no, but that is definitely in the works. And as I said, as a temporary fix, you can kind of use what time series offers out of the box. But yes, that is in the works. These functionalities are in version 13, not 12.3. Well, some of them are in version 13. Some of them are also in 12.3. I think animation video and frameless video should be there in 12.3. If you have a multi-core CPU, do you need to use parallelize? Yes, yes, you do need to use parallelize if you want generation to be actually happening in different kernels. Is there a table in the documentation comparing these functions with respect which ones get stored in memory and which don't? There isn't. That is a really good suggestion. We should definitely have that. And I think these, oh, does any video function use the new compiler? If so, which parts? Not yet. That is definitely something that we want to include as well. Yep, standard transitions, those are the ones that, as I said, are in the works. And I think that is all. Thank you very much.
Carlo, there's one more question from Christopher in the Zoom chat. Is there a performance memory cost to using animated image?
So animated image, what it does is it extracts the frames and it burns them into the notebook. So yes, you will make your notebook giant if you don't pay attention. Some workarounds for that is to make sure to select a low frame rate and select a small raster size. That will minimize the footprint of the stored animated image in the notebook. One thing that is being discussed is how to make the footprint of image in the notebook smaller. So when that will happen, automatically we will get the same benefits in animated image. I think that is it. Thank you very much to everyone, and I'll see you hopefully in our office hour for the sound and vision team that will happen in about 1 hour. Thank you very much.